Hello everyone, welcome back to the CAE-SHOP channel. In previous videos, I have introduced some problems using arbitrary Lagrangian relational map. In this video, will be one such thing is the ALE map, but we had an additional map movement control along with setting constraints between Lagrangian and ALE map. Let's try it. I will draw the geometry in Space-Column. I will draw the geometry on XY plane. The model will have three bodies. The first is the thin plate at the bottom. A square to represent an upside like a bird. It will impact to the stem. And the third is the air or vacuum around the square body. The first, I will draw the square and body around the square first. The dimension is 100 and 100. The distance between below the square and the x direction is 25. One, two, five. The distance with y is about 50. And another body is around the square. The dimension is 200. Square within at the center. Okay. I will use a small technique to represent a 2D dimension problem. Here is 10 or 5 millimeter. 5 millimeter. This is the air around the object. So we need to create the object inside. Here I will copy this file by Ctrl+C and Ctrl+V. Hide the body and pull this file up to 100 millimeter. Okay, we will have here two body. Here is a vacuum, and here is a bird, or I will use a water material. Now we need to create a thin plate by using the bottom face of the vacuum body here. Ctrl+C and Ctrl+V. Then I will extend two sides. Pull, select an add, and extend to 50 millimeter. And for another side. Okay, here is a stain. In this model, the vacuum and water will be arbitrary Lagrange relations. They are multi-material, so we need to combine two bodies into one part, or the node between at interface between two bodies is a merge node. Okay. Select two bodies, right-click, and move to a new component. Here we need to set share topology to share. Okay, that is okay. Close the geometry. Now we need to define material. For the stain body, we can still use a structure stain, but we need to provide a new property. Here is a bilinear kinematic hardening. Here in the plasticity, we can add a new bilinear kinematic hardening. Here shown is 500 megapascal, and for torsion modulus is 20 megapascal. Okay, you can delete some as a material property. We don't need them. The next is a vacuum. You can use a vacuum model here. It's a Laplacian vacuum. Density equals 0. And another material is the water. I will use mass null. Density equals 1000. As a property gives a default, and if the equation of state here Grunaysin, and value for C coefficient here is 1500 meter per second. Okay, close the material and double click to open the mechanical. The first, we need to assign material for each body corresponding. Here for the vacuum, we change from structure stain to vacuum. And water. For the plate, we will stain to use a structure stain, so we don't need to change it. And the thickness here equals 5 mm. The next is a connection. For the contact or interaction between ALE and the Lagrangian, we don't use body interaction or contraction, so I will delete them. In the case, if you have only one ALE body and contact with an Lagrangian, here you can use the coupling contact. But this feature has some limit option for the multi-material or multi-ALE body here. So I will not use the coupling here. Instead, I will use the control command. Instead, I will use the command to control the contact between ALE and Lagrangian. In the math, here I will use 5 mm for element size. You can use a small value for the better. For the boundary condition, the first I will fix two ends of the plate here by selecting 4 points in the two end sides. Insert fixed support. This model is a represent for the 2D, so we need to constrain the body in the Z direction. Here we can use the displacement condition. First, we will apply for the face. Apply Z component equals 0. And the next development for 2S here. 2F of the plate and the Z equals 0. Okay. The next, we need to change default section control from finite element to the ALE. Here I will insert a section. Apply for two body here. Method finite element to ALE. Here we have two body with two different material. So we need to change formulation to one point ALE multi-material element. ID element. For the plate, here is a deformed body, a flexible body. So we need to increase integration point for the better result. So I will use another section. Apply for the thin body and change integration point in the thickness from 1 to 3. Here 3 integration point in the thickness. The hourglass control for the ALE body is a type standard and a small value hourglass coefficient 1e-6. And the second hourglass control for the plate type 1 0.03. In analysis setting, I will consider the problem in the 0.4 millisecond. Here I use the millisecond metric. The value here equals 0.4 millisecond. Reduce the safety factor to 0.7. Increase number of CPU depend on the hardware. In the ALE control, affection method change to run the plate half index shift for the second order accurate. Okay, the next we need to define constraint or interaction between ALE and Lagrangian. Click on the Add-on tab and active QF Manager. Click on this one time. Here is already activated. Back to the environment. Select Keyword Manager. First, we need to constraint Lagrangian in solid. Title any name. Geometry first is a Lagrangian, and second, your matter is a ALE body. Here, two body. In the middle, a load curve not used, and geometry for band 90 not used. In this interaction, we had two materials, but the main interaction is here between here water and the plate. So here multi-material option, I will change from 0. 0 means that interaction between Lagrange and own ALE body. I will change to 1. It means that the interaction is only between Lagrange and the higher density or body with higher density. Here is a MC-M coupling equal 1 coupled with material with high density. Fluid structure coupling method change to penalty coupling for cell and solid element. Therefore, in normalization and compression only. Okay. For the movement of ALE mat, we need another control. Here is ALE multi-material group. Sorry. ALE reference system group, not multi-material. Here is the ALE reference. Geometry is a two ALE body. Reference system type is an automatic mass motion following mass weighted. Constraint here BC translation, no constraint. For the expansion, constraint in the X and Y expansion, and constraint on rotation direction. Okay, let's try to solve the problem. The solution is a finite. Let's check some result. Here is a total deformation for all body, and another the total deformation for the plate body only. Okay. Don't have any result. Here, sorry, I forgot the initial condition. So we need to define initial velocity for two ALE body. Velocity in the minus y direction. The velocity will be equal 140 meter per second minus 150 millimeter per millisecond or 150 meter per second. And check one time again about the constraint Lagrangian in solid. Here, coupling direction, I think we need to change to default. If the fork is applied in the global direction. Give another the default. Okay, let's solve the problem. And check the formation of the plate. Okay, it looks good. Here, let's see the deform input. Okay, let's check another result. By right click, insert an user-defined result. Expression here is a pressure. Let's see. Create one time again. Pressure. Wait for the ALE body. And another result is a volume fraction. Here is a volume fraction. Okay, so in this problem, I will introduce two options. The first is a constraint Lagrangian in solid by user comment here. In the simple case, you can use a coupling control here. But it's a recommend to use this option or this feature for the problem with only one ALE body. For multi-material ALE, so I recommend to use a constraint Lagrange in solid option here. And the second option is the ALE difference system group to modeling the movement of ALE mass. Okay, so that's all in the problem. Thank you.